The first thing we need to do is make sure we're all on the same page in terms of our definition of an electric circuit. So to begin with, our working definition of a circuit is simply going to be a path for transmitting electric current. Electrons, if they are located in a region they don't want to be, and you give them a pathway towards a location where they do want to be, maybe away from other electrons and towards, a space that has very few electrons and a lot of protons. If you connect those 2 points with some kind of conductive pathway, electrons will flow from the area that they don't want to be in to the area that they do want to be in, or from an area of high voltage to an area of low voltage. So that's going to be our working definition of circuit, a connected pathway that allows electrons to move from higher voltage to lower voltage, or an area they don't want to be in to an area they would prefer to be in. We have 3 requirements, and we'll take a look at each of these individually. They are a power source. You need something to create the voltage in the circuit, whether it be a battery, a wall outlet, a generator, etc. You need something that generates this potential difference, this voltage difference, which will then cause electrons to flow. You need some conductive wire, so you need some kind of metal wire or something along those lines that will allow electrons to pass through them from the area of high to low voltage. And last would be what we call a load or a resistor. There's several other things that we could put into the circuit, but we're only going to be looking at like resistors or what we call a load, and that's anything that the circuit is powering. So a light bulb, a phone, a microwave, etc. Anything that you're kind of plugging in to convert into some kind of energy, light energy, sound energy, etc. So to take a look at each of these, let's start with a battery first, because I don't think most people fully understand how a battery actually works. A lot of people tend to think that a battery has a certain number of electrons in it, and once it spends all its electrons, then the battery is dead and you have to throw it out. It has no more electrons. It ran out of electrons. And that's not in any way what's actually happening here. A dead battery has essentially just as many electrons as it had when it was freshly charged. It has to do with where those electrons are. So if we think about this, if you kind of think about a little nub that sticks out on a lot of batteries, well, that's connected to a piece of metal on the inside that, due to a chemical reaction, has had a lot of its electrons removed. So that is basically a very, very positively charged metallic rod. Now that's separated from the rest of the battery along the outside, which, due to this chemical reaction that pulled these electrons out of the positive rod in the middle, well, it moved them outside to that kind of like that negative bath of electrons. So what we essentially have is the center part of the battery is positively charged, and the outer part, or the outer diameter, is negatively charged. Now if we kind of zoom in here, what you'll see is there's this kind of blue barrier between them, and that's a chemical barricade, and it basically does not allow electrons to just flow straight across. It's kind of like a one-way road. If you have electrons in the positive section, there's a chemical reaction that will move them over to the right side, but they cannot go back the other way. It's not a reverse chemical reaction. All right, so let me show you in a little more detail. If we connect both sides of that battery with a conductive pathway, you'll notice at the top that conductive pathway is in contact with the positively charged rod, and on the bottom it's connected with the negatively charged region. So what's going to start to happen is electrons, they're crammed into this negatively charged kind of like lavender section. They want out. They would rather be near the positive. So they're going to flow through that wire and go to the positive region. So if you take a look on the left, oh, my bad, you'll notice that some electrons will start to appear in that section, that red positive section. Now that is going to engage that chemical reaction. And what's going to happen is anytime electrons start to appear in that positive section, well, to simplify it, we're going to call it chemical A and chemical B. They basically react with one another in the electrons. If you take a little of chemical A, a little of chemical B, and you add some electrons, you basically are going to do 2 things. You're going to get chemical C, so whatever the resultant of that reaction is, you get chemical C, we'll call it. But you also get one of those electrons moved back over in that one-way direction to the negative terminal. So in doing this, every time electrons enter the positive section, this chemical reaction is triggered, and they get moved across that chemical barricade, and they wind up on the outside section of that battery, and once again you maintain your positive and your negative section. All right, so if you can wrap your head around that a little bit, we'll try and explain what happens when a battery dies. So if we take a look here, we have a better understanding that the electrons are going from the outer negative section through that conductive wire and landing in the positive section. Well, every time that an electron goes into that positive section, it triggers that chemical reaction. And what happens is, over time, you have less and less of chemical A and B, because they are reacting to move these electrons over, and you're producing more and more of chemical C. Now again, I'm not using the actual names, it depends on the battery, but you can hopefully understand that as time goes by, I am losing the chemicals I need to move the electrons over, and I'm just winding up with this resultant which cannot move electrons. So realize that A and B can react to transport electrons across that barricade, but C can't. So we literally have a limited supply of these chemicals, and once we run out of them, we no longer have any ability to move these electrons over. And that's when a battery dies. The battery dies when it runs out of the chemical energy it needs to keep moving those electrons over. But every time one electron moves through the pathway and jumps into the positive section, well, that chemical reaction has taken an electron that already got there and moved it back over. So the electrons kind of go through the whole pathway, jump into the positive section. They're like, oh, I'm here, this is great. Boom, next thing you know, that chemical reaction pulls them across. They're like, what am I doing back in the negative section? And they go through that circuit again. And this repeats over and over and over. So you're basically reusing the same electrons. You're just tricking them, and as soon as they get into the positive section, they get transported back over, and they go through that process over and over. Once you run out of A and B, well, then the electrons that start getting into the positive section at that point, they now stay there. And it's only a matter of time before the positive section gains enough electrons that can no longer be transferred out, where you get both the inner rod and the outer area of that battery. They have the same charge, and no electrons will move anymore. That's the point where a battery has quote unquote died, and it's no longer usable, unless of course it's a rechargeable battery. All right, so how do light bulbs work? We're going to be using batteries, we're going to be using light bulbs, so we should probably make sure we understand how these two things operate. So I'll go through the basic structure of an incandescent light bulb, kind of the older ones, and we'll use that to try and test your understanding of how all this works. So what we want to realize before I go into this is you want to realize that the bottom of the bulb is actually extremely important. So many people think it's just designed so that it can kind of screw into the socket and be held in place, but it's actually the primary reason a light bulb works. So we have to realize it's kind of hard to see without showing you an actual light bulb. But the very bottom section, if you look at the bottom of a light bulb, it's a conductor, it's a piece of metal. That black piece there is an insulator, and then the actual part that screws into the socket itself is always made of metal, and it's also a conductor. So what you'll notice here is we basically have an insulator sandwich. We've got conductors on either side with the insulator in the middle. And that's really important because that insulator does not allow electrons to flow directly from the section that screws into the socket to the section at the bottom of the bulb. Those two are connected by the filament that goes through the bulb. So I'm trying to show you the inside of the bulb here, but that very bottom section runs up, goes through that kind of filament loop, and then comes back down and connects on the side. Now, some people may say, well, how can it go straight up? There's an insulator in the way. And that's because that insulator, if you were to pull it out and look at it from the top view, it has a hole in the middle. So that wire on the bottom, that pink wire, goes up through that hole, goes through the filament, and then it comes back down, and it doesn't connect to the bottom anymore, it connects to the side. By keeping that insulating donut, essentially, it ensures that the only pathway an electron can take if it wants to go through this bulb is up through the bottom, through the filament, and then down through the side. So that socket, that part that screws into the socket, is actually one of the connections. You need two connections, positive, negative. That's one of the connections of the bulb. If you were to replace that with a plastic piece, this light bulb would no longer work. All right, so let's take a look at some of these. So if we were to connect, let's say, a positive and a negative wire, and that's essentially what happens when you're screwing this light bulb in. In this case, we'll say the negative section is coming in the bottom, and the positive section is coming in the top. Well, now if we turn that on, electrons will flow from the negative section. They'd love nothing more than to jump right to that positive wire, but because of that insulating little donut piece, the electron only has one choice. Go up through the hole in that little donut, go through the filament producing the light, go back down, and then leave through the actual part that's screwed into the socket. So that light bulb will now operate. If, however, we took the two wires, the positive and the negative, and we just touched both of them to the bottom piece, as I've done here, you'll notice that the electrons, because they don't have to, go through the light bulb, they will simply go into the bottom section and say, wait a minute, the positive is literally right here, and they will just go right through. So that light bulb will not light because you're not forcing the electrons to have to go through the filament. You're basically taking a light bulb and just putting it next to a wire, but there's no reason for any electrons to flow in there. Likewise, if I connected the negative and the positive like such, remember that whole entire piece that screws into the socket is a conductor. In a case like this, you also wouldn't have it light because the electrons could literally jump right through that conducting piece. That's why the insulating donut piece is so important. It forces the electrons to have to go through the filament to get from one of those two conductors to the other. So this is the only way that you can actually set it up so that they are forced to go through the light bulb, through the filament, in order to get to the side that they want to.